Okay, this section of the textbook is called atomic weights. There is a unit called the atomic mass unit, which is equal to 1/12 the mass of carbon-12. As we saw in the last section, carbon actually has a couple different isotopes, so we're specifying that this is 1/12 the mass of the carbon-12, which is the most common of carbons. And then you have atomic mass, or atomic weight, to be called both, which is the average atomic mass for all the naturally occurring element, expressed in atomic mass units. So in order to come up with the atomic mass or atomic weight, you do a measurement of the isotopes done with a mass spectrometer, and that is what's shown down here. This is isotopes in neon. There are 3 isotopes. You notice they all have the 10 protons, but the difference is that this one has 12, so it has an atomic mass of 22. This one has 11, so it has an atomic mass of 21, and this one has 10, so it has an atomic mass. Mass of 20. Okay. And when we do a mass spec of this is what we get, okay? So the 20, this one here, 0.9051 of all the atoms that they tested had this atomic mass, okay? And then 0.0027 had a mass of 21, and 0.0922 had atomic mass of 22. Now, these 0.9051, the 0.0027, and the 0.0922 are what they call the fractional abundance, which is the fraction of the numbers that compose a particular isotope. Now, this is fractional abundance. I can also have percent abundance by simply multiplying each one of these by 90. So as fractional abundance, these have to add up to be 1. As percents, this would be just multiplied by 100, so 90.51, 0.27, and 9.22. And when I add those up, you'll see that if I do it with the decimal place, it'll add up to be 1. If I do it with the percents, it adds up to be 100. So how do you do this? So number 52 in the book says an isotope of 2 naturally occurring isotopes has the following abundances. So it gives me the isotope mass. You'll notice that they don't add up to be exactly 50, and the reason that is because of Einstein's mass is energy is equal to mass times the speed of light. So basically, by having the mass is a little bit less than that of the absolute addition of protons and neutrons, and it has a fractional abundance of 2.5 times 10 to the minus 3, and then the other isotope is 50.94440, and it has a mass of 99. Now, just looking at these and looking at these fractional abundance, I can see that most of this mass comes from basically the isotope of 51, okay, and a very small portion from the portion of 50. But the way that I calculate what the actual atomic mass is I multiply the 49.9472, so multiply, times the 2.5 times 10 to the minus third, and I get 0.1249. I do the same thing for the 50.944. I multiply times the 0.9975, and I get 50.82. And if I have more isotopes, I would continue to do that. This one only had 2, and so at that point I add them up, and I get 50.94, and the units for these problems is AMU. And a lot of times they'll ask what is the identity, so I look at the periodic table. What has an atomic weight of 50.94 on the periodic table? And it is vanadium. Number 54 has 3 naturally occurring isotopes. This would be basically 28, this would be 29, and this would be 30. Okay, again, the one with the highest fractional abundance is this 28, so it's going to be somewhere around 28. Okay, but I do the same thing. I'm going to multiply 27.977 times 0.921221, and I get 25.80. 28.976 times 0.0470 gives me 1.362. 29.974 times 0.0309 is equal to 0.9262. And then I add up these 3, so 25.80 plus 1.362 plus 0.9262 gives me 28.09. And again, units are AMU. I mentioned this in class the other day that basically when I'm grading tests or assignments, the answer is worth 1 to 2 points depending on the total points of the question, but the units are always worth 1, so it's important to identify what the units are. And if I want to know what this element is, I can look on the periodic table for 28.09 and I come up with silicon. And that's how you calculate the atomic weight that you see on the periodic table there. And that's the end of this section.